Close your eyes and imagine the deepest silence you have ever known, a place where even light itself cannot escape. For billions of years, these cosmic giants have ruled the universe, black holes, the ultimate trap for matter, energy, and even time. But what if even the darkest objects are not eternal? What if, far beyond our lifetimes, far beyond the lifespan of stars, every black hole will slowly fade, releasing its energy back into the void? Tonight, we begin a journey into the final chapter of their existence. We will travel back to the violent birth of black holes, to the core of collapsed stars where gravity crushes matter beyond imagination. We will stand at the edge of the event horizon, where time slows and light bends, and then move forward to the theories that shook the world of physics, Stephen Hawking's revolutionary idea that black holes are not forever. Through the quiet lens of quantum physics, you will hear the story of Hawking radiation, the faint whisper of particles escaping from what was once thought to be an inescapable prison. This process, invisible yet inevitable, promises that even the darkest objects in the cosmos have an ending, a slow evaporation that spans trillions upon trillions of years. As you listen, let the rhythm of the universe guide you. Feel the pull of gravity as we journey to a future so distant that galaxies have faded, stars have cooled, and black holes, the last architects of the cosmos, begin their final act. This is the story of endings on a cosmic scale, the death of darkness itself, and perhaps the ultimate reminder that nothing, not even a black hole, lasts forever. Chapter 1: Birth of Darkness. Long before black holes haunt the edges of galaxies, their story begins with the life of a massive star. Picture a giant star, tens of times heavier than our Sun, burning so fiercely that it bends space with its own gravity. For millions of years it shines, a brilliant furnace of fusion, fusing hydrogen into helium and then into heavier elements, sustaining its radiant glow. But no fire lasts forever. As the core's fuel thins, the delicate balance between radiation pressure and gravity begins to fail. The star's heart contracts, and gravity, relentless and patient, takes control. Within minutes, the inner layers collapse inward with unimaginable force. Temperatures soar to billions of degrees as protons and electrons are crushed into neutrons. The star trembles in its final breath, and then, in one cataclysmic instant, its outer layers explode outward in a supernova so bright it can outshine an entire galaxy. The supernova is spectacular, scattering gold, iron, and the building blocks of life into the cosmos. But the core, the heart of the star, does not escape. Under crushing gravity, it collapses further and further, shrinking beyond the limits of ordinary physics. Atoms are stripped of their identity. Matter folds into a density so extreme that space and time themselves curve inward. This is the birth cry of a black hole, a place where gravity is so absolute that nothing, not even light, can flee its grasp. From the outside, there is no flash of warning, no blazing signature in the sky. The newborn black hole is silent, invisible, a dark sphere defined not by what it shows, but by what it hides. Astronomers call the boundary of this region the event horizon, a one-way door through which matter and energy can enter but never return. Beyond this edge, the normal rules of time and space cease to exist. The surrounding galaxy might not even notice at first. But within that small, dense point, gravity reigns with an iron will. Stars that stray too close will be stretched, shredded, and swallowed. Gas clouds will spiral inward, heating to millions of degrees as they vanish past the horizon. To an outside observer, the black hole appears eternal, an unblinking eye of infinite darkness. From the moment of its creation, the black hole becomes a silent architect of its surroundings. Its gravity warps the very fabric of space-time, bending light into arcs and twisting the paths of nearby stars. Astronomers call it the ultimate cosmic predator, invisible, patient, and endlessly hungry. Around some black holes, matter forms a glowing accretion disk, gas and dust spiraling inward at nearly the speed of light, heated until it shines brighter than 1,000 suns. Jets of plasma erupt from the poles, stretching for light years, as if the black hole were both devouring and creating at once. These jets, paradoxically, seed galaxies with energy and elements, proving that even in destruction there is creation. Yet the heart of the black hole remains unknowable. Inside the event horizon, Time and space fold in on themselves. According to Einstein's equations, all paths lead inward to a singularity, a point of infinite density where the known laws of physics no longer apply. For an outside observer, anything falling toward that point appears to slow, frozen in time, light stretched into eternity. But to the falling object, the crossing happens in an instant, a silent plunge beyond the reach of the universe. For billions, perhaps trillions of years, a black hole can persist like this, feeding, spinning, shaping the galaxies around it. It seems immortal, a permanent scar on the cosmos, a place where beginnings and endings blur. To gaze into such darkness is to feel the weight of infinity, and yet, as we will soon discover, even these titans are not eternal. Their apparent immortality hides a quiet truth, one uncovered only in the last century, that black holes are not the final word of creation, but a chapter in a much longer story, a story of energy, of quantum whispers, and of a slow, inevitable fading. As we continue our journey, we will follow the clues left by the greatest minds of physics and trace the delicate radiation that signals the black hole's eventual demise. But for now, remember this beginning. A black hole is born not in silence, but in the furious death of a star, a cosmic echo of both violence and infinite calm. Chapter 2. Anatomy of Darkness. Now that a black hole has been born, we move closer, into the silent geometry of its being. From a distance, it appears simple, a perfect black sphere against the backdrop of stars. But approach the event horizon, and that simplicity dissolves into complexity. The first thing you notice is the accretion disk, a luminous ring of gas and dust spiraling inward at nearly the speed of light. As matter falls, it heats to millions of degrees, glowing in X-rays more brilliant than 1,000 suns. This is the paradox of a black hole, invisible at its core, yet capable of creating the brightest beacons in the universe. Just beyond the disk lies the photon sphere, a region where light itself orbits in endless circles. Here, gravity is so strong that photons, particles of pure light, are caught in a perpetual loop, creating a shimmering halo that astronomers glimpse as a faint outline against the void. Time stretches as you approach, seconds elongating, clocks slowing, until moments begin to feel eternal. The event horizon marks the point of no return. It is not a surface in the usual sense, no solid wall or barrier. It is a boundary in space-time where escape velocity exceeds the speed of light. To an outside observer, anything crossing this threshold appears to slow and fade, forever frozen in time. But for the falling object, the crossing is instantaneous, a seamless step into the unknown. Inside, beyond what we can see, lies the singularity, a region of infinite density and zero volume where space and time collapse into a single, unknowable point. Here, the known laws of physics break apart. Relativity can describe the curvature of space-time, but not what happens when that curvature becomes infinite. Quantum mechanics offers no easy answers. This is not just a place, it is a question. What lies beyond the singularity? A gateway to another universe, a hidden dimension, or simply an end, a boundary where our understanding stops and silence begins? Beyond the event horizon's invisible threshold, the black hole continues to shape the universe around it in unexpected ways. Though nothing escapes its grasp, the region nearby pulses with activity, streams of matter twisting into dazzling forms as they spiral toward their end. From the poles of some black holes, immense relativistic jets burst forth, narrow beams of particles propelled outward at nearly the speed of light. How can something so powerful escape the grip of gravity? It is not the black hole itself releasing them, but the chaotic magnetic fields of the accretion disk, where superheated plasma whirls and twists before crossing the point of no return. These jets stretch across light years, seeding galaxies with energy, shaping the birth of stars far beyond their origin. The black hole's spin is another hidden force. Many black holes rotate at incredible speeds, dragging space-time with them in a phenomenon called frame dragging. This cosmic whirlpool can twist entire regions of space, creating eddies of gravity that influence everything nearby. Even time itself cannot resist the pull. Clocks near the event horizon tick slower than those farther away. To an outside observer, an object falling in appears to freeze at the edge, its final moments stretched across eternity. But for the falling object, the descent is swift and absolute. Inside, where our equations fail, lies the singularity, a point where density and gravity climb beyond infinity. Some theorists wonder if this singularity could connect to another universe, or if it represents a true end, a place where space and time simply stop. Quantum gravity may one day reveal the truth, but for now it remains the deepest mystery of all. And yet, despite their hidden cause, black holes are not silent. They shape galaxies, feed on stars, and power some of the brightest phenomena in the universe. Around these dark hearts, light bends, matter dances, and the fabric of space-time itself is sculpted into forms stranger than any dream. This is the paradox of a black hole, a place of absolute darkness that illuminates the cosmos with its power. To understand their eventual death, we must first understand this living architecture of gravity and light, a masterpiece of destruction and creation that begins our journey into their ultimate fate. Chapter 3: The Paradox of Eternity. For much of human history, black holes were thought to be eternal. After all, how could anything so powerful, so absolute in its gravity, ever fade? From the moment the idea of a black hole emerged, it carried with it a kind of cosmic permanence. Albert Einstein's theory of general relativity painted them as perfect one-way doors. Once matter crossed the event horizon, it was lost to the universe forever. No signal could escape, no information could return. To scientists of the early 20th century, this meant black holes could only grow larger, devouring matter and energy until the end of time. Their nature reinforced the illusion of immortality. Every star that wandered too close, every cloud of gas that drifted inward, only fed their mass. Instead of aging, they became stronger. The mathematics of gravity offered no mechanism for decay. If left alone in an expanding universe, a black hole would simply persist, dark and unchanging, long after the last star flickered out. To imagine their scale is to feel the weight of infinity. A stellar mass black hole might be only a few kilometers wide, but its gravity is so immense that nothing, not even light, can escape. Supermassive black holes at the centers of galaxies hold millions or even billions of solar masses, anchoring spiral arms of stars for eons. Their existence seemed to mock the idea of an ending. For decades, scientists debated whether black holes represented the ultimate dead end of physics. Were they the final stage of matter? Would they survive until the universe's last breath, outlasting even the heat death of space itself? These questions lingered like distant echoes, waiting for a mind bold enough to challenge the very concept of eternity. Yet, as the 20th century unfolded, cracks began to appear in the idea of eternal black holes. The rise of quantum mechanics introduced a new set of rules, strange, counterintuitive, and impossible to ignore. Unlike the smooth curves of Einstein's relativity, the quantum world is restless, filled with uncertainty and tiny fluctuations that never stand still. Physicists began to wonder, could the vacuum of space around a black hole be as empty as it seemed? Quantum theory says no. Even in perfect darkness, space is alive with virtual particles, pairs of matter and antimatter flickering into existence for the briefest moments before annihilating each other. Usually these pairs appear and vanish without consequence. But near the event horizon, where gravity bends everything, the dance changes. Imagine a pair of virtual particles forming right at the edge of the black hole. Normally they would meet and cancel out, leaving no trace. But the black hole's gravity can pull them apart before they reunite. One particle slips inside, lost forever, while the other escapes into space as real radiation. To a distant observer, it seems as if the black hole itself has emitted a particle. This insight, both daring and elegant, came from Stephen Hawking in 1974. He proposed that black holes are not perfect prisons, but slow evaporators, leaking a faint glow of energy now known as Hawking radiation. Over unimaginable spans of time, this radiation carries away mass, causing the black hole to shrink, fade, and ultimately vanish. The discovery stunned the scientific world. Here was a bridge between quantum mechanics and general relativity, between the smallest scales of the universe and its most massive objects. It suggested that even the darkest, most powerful entities are not forever. Given enough time, far longer than the current age of the cosmos, black holes must die. This revelation transformed black holes from eternal monuments of gravity into dynamic, mortal participants in the cosmic story. The paradox of eternity had been broken. The universe, it seemed, allows nothing to last forever. Not stars, not galaxies, not even the very darkness that once promised infinity. Chapter 4. Stephen Hawking's Insight. The year was 1974. In a quiet Cambridge office, a young physicist named Stephen Hawking stared at the equations of the universe and asked a question few dared to ask. What happens at the edge of a black hole when quantum mechanics meets general relativity? Until then, black holes were described only by Einstein's theory. Perfectly dark, perfectly silent, eternal. But Hawking, blending the unpredictable world of quantum physics with the smooth geometry of space-time, saw something extraordinary. According to quantum mechanics, empty space is never truly empty. Even in a perfect vacuum, virtual particles constantly flicker into existence as particle-antiparticle pairs, appearing and annihilating in fractions of a second. Normally, these brief visitors leave no mark. But Hawking realized that near the event horizon, gravity could separate the pair before they cancelled each other out. One particle might be pulled into the black hole, while the other escaped into space as real radiation. To an outside observer, it would appear as though the black hole itself was emitting particles, slowly, invisibly, bleeding energy into the universe. This became known as Hawking radiation. The idea was radical. If a black hole radiates energy, it must also lose mass, and if it loses mass, it cannot be eternal. Over unimaginable spans of time, it would shrink, heat up, and eventually vanish in a final flash of pure energy. Hawking's calculation was meticulous. He showed that the temperature of this radiation depends on the mass of the black hole. A giant supermassive black hole would emit almost no detectable radiation, and would take trillions upon trillions of years to fade, while a tiny black hole would evaporate much faster, releasing a torrent of high-energy particles in its last moments. This revelation shook the foundations of physics. It forced scientists to reconsider what a black hole really is, not an inescapable void, but a slow-burning ember of cosmic fire. The boundary between reality and theory had shifted, and with it, our understanding of the ultimate fate of the universe itself. Stephen Hawking's proposal did more than show that black holes could die. It forced physicists to confront one of the greatest puzzles in modern science, the fate of information. According to quantum theory, information about particles, about states of matter, cannot be destroyed. But if a black hole evaporates entirely, what happens to the information carried by everything it swallowed? Does it vanish forever into nothingness, defying the rules of quantum mechanics? Or is it somehow preserved, hidden in the faint glow of Hawking radiation? This paradox split the scientific world. Some argued that information must be lost, making black holes cosmic erasers of memory. Others believed that information is encoded at the event horizon itself, perhaps stored in a thin layer of quantum bits, a theory that later grew into the holographic principle, the idea that the universe may be a vast projection of information inscribed on its boundaries. Hawking radiation also tied black holes to the second law of thermodynamics. Physicist Jacob Bekenstein had earlier suggested that a black hole's surface area could be linked to entropy, a measure of disorder. Hawking's work confirmed this. Black holes have entropy, and they radiate heat. They are not silent abysses but thermodynamic objects that obey the same rules as everything else in the universe. The implications were staggering. A black hole is no longer just a grave for matter. It is a laboratory of quantum gravity, a cosmic furnace where the laws of the very large and the very small collide. To study their evaporation is to glimpse the unification of physics itself, where Einstein's curved space-time meets the restless uncertainty of quantum mechanics. What began as a theoretical exercise in the mind of a young physicist reshaped our entire vision of the cosmos. No longer immortal, black holes became part of the universal cycle of birth, life, and death. They too must fade, their titanic shadows eventually dissolving into a whisper of light. Chapter 5. Hawking Radiation Explained. Now that we've followed Stephen Hawking's insight, it's time to explore how black holes actually lose mass. The process sounds almost impossible, something so massive, so dark, quietly evaporating into the cold vacuum of space. Yet quantum mechanics paints a picture that is both subtle and profound. At the edge of the event horizon, space-time is never empty. It is alive with the flicker of virtual particle pairs, constantly appearing and annihilating within fractions of a second. Under normal circumstances, these pairs meet and vanish, leaving no trace, but a black hole bends the rules. Picture one of these pairs forming right at the horizon. Normally they exist only as possibilities, not real matter. But if the black hole's gravity pulls them apart, one particle may slip inside while the other escapes outward before the reunion. When the escaping particle breaks free, it becomes real, a quantum of radiation we can, in theory, detect. Its partner, swallowed by the black hole, carries negative energy relative to the outside universe, effectively reducing the black hole's total mass. This is the essence of Hawking radiation, a slow leak of energy, born not from the black hole itself but from the restless fabric of space around it. It is not a beam of light or a violent flare but a faint ghostly glow, photons, neutrinos and other particles whispering into the void. The temperature of this radiation is astonishingly low for large black holes. A black hole the mass of our Sun radiates at less than 1/millionth of a degree above absolute zero, colder than the cosmic microwave background itself. This means that for billions of years such black holes absorb more radiation from the universe than they emit, effectively gaining mass rather than losing it. But as the universe ages and cools, this balance will shift. Eons from now, when the cosmic background fades to near nothing, Hawking radiation will dominate. The black hole will begin its slow retreat, shrinking imperceptibly as it surrenders its energy to the dark. As the eons stretch into unimaginable spans, the black hole's slow fade becomes a race toward a dramatic end. The more mass a black hole loses, the hotter it becomes. Unlike a star which cools as it burns out, a black hole grows increasingly energetic as it shrinks. Its temperature rises, its radiation intensifies, and the once silent darkness begins to stir with a faint lethal light. For a supermassive black hole millions of times the mass of our Sun, this process is glacial. It will take 1067 years or more before Hawking radiation overtakes the cosmic background and the true evaporation begins. But as the final stages approach, time accelerates. The black hole shrinks rapidly, the radiation becoming fierce and violent. In its last seconds, it releases a blinding burst of high-energy particles, gamma rays, neutrinos and photons, in a brilliant flash that outshines entire galaxies. What once devoured light ends its life by flooding the universe with it. This ultimate explosion is not a supernova or a conventional detonation. It is the final whisper of quantum mechanics, the pure conversion of mass to energy predicted by Einstein's EIMC2. The singularity, that infinite knot of space and time, vanishes, leaving nothing behind but a faint ripple of energy and a memory etched in the fabric of space-time. What remains is silence. The black hole is gone. No remnant, no core, no trace of the immense gravity that once ruled its surroundings. Only the faint radiation it released into the cold void, spreading outward for eternity, carries the story of its existence. And so, the most mysterious objects in the cosmos, the great devourers of light and matter, are revealed to be mortal after all. Hawking radiation is the slow clock ticking at the heart of every black hole, a promise that even the universe's darkest giants must someday give back the energy they have borrowed. Chapter 6. The Life Cycle of a Black Hole. Every black hole begins as a death, and ends as a slow surrender. To understand its entire journey, we must trace its life from the violent birth of a collapsing star to the final whisper of Hawking radiation. A black hole is born when a massive star exhausts its fuel and its core collapses under gravity's relentless pull. For millions, even billions, of years after that explosive beginning, the black hole grows. It feeds on gas clouds, swallows wandering stars and merges with other black holes. Each collision adds more mass, deepening its gravity well and expanding its event horizon. During this growth phase, a black hole is at its most active, its accretion disk blazing with X-rays and radio waves, powerful jets streaking across interstellar space. For a supermassive black hole in the heart of a galaxy, this feeding period can last longer than the lifespan of all the stars around it. It becomes an anchor for galaxies, shaping the motion of stars and influencing the birth of new ones. Astronomers believe that many of the luminous quasars we observe in the distant universe are the signature of black holes in this voracious youth. But eventually the galaxy grows quiet, gas becomes scarce, stars drift away. The black hole's feast slows to a crawl. For billions of years it will sit in apparent silence, no longer gaining mass but holding steady, a dark, unblinking monument to gravity. This is the middle age of a black hole, immense, stable, and seemingly eternal. Yet the clock of Hawking radiation is always ticking. As the universe expands and cools, the faint radiation will one day surpass the background heat of space. From that moment onward, the black hole begins to lose more energy than it gains. It enters its final stage, evaporation. At first the loss is imperceptible, atoms of mass drifting away as radiation over unimaginable timescales. This is the beginning of the end, a quiet erosion that will eventually accelerate into a dramatic finale. As the ages of the universe pass, the black hole's slow evaporation becomes the defining force of its existence. The cosmic background cools until it can no longer feed the black hole, and the faint whisper of Hawking radiation grows stronger. What once seemed eternal begins to thin, particle by particle, photon by photon. At first, the process is invisible, a quiet erosion stretching across timespans that dwarf the life of galaxies. For billions of years, the black hole shrinks so slowly that even the stars around it could be born and die many times without noticing a change. But the pace is not constant. The smaller the black hole becomes, the hotter and more energetic it grows. Eventually, in the universe's unimaginable future, the black hole enters its final act. Its temperature skyrockets. Its Hawking radiation blazes with a fierce intensity, releasing X-rays and gamma rays in a storm of pure energy. In the last seconds of its life, the black hole shines brighter than the galaxies it once influenced. A final outpouring of light from an object that once consumed it. Then comes the end. The event horizon contracts to nothing. The singularity, that knot of infinite density, dissolves into a flash of pure radiation. No remnant remains, no core, no shadow, only a faint echo in the fabric of space-time. This is the ultimate destiny of every black hole. Not an endless reign of darkness, but a return of energy to the cosmos. The giant that once devoured stars and shaped galaxies gives everything back, a silent acknowledgement that even the mightiest forces are temporary. The black hole's death is not a tragedy. It is a transformation, a reminder that nothing in the universe is forever. Chapter 7. The Final Moments. The black hole has spent eons fading, particle by particle, into the silence of the universe. Now only a faint shadow remains, a remnant no larger than a mountain, yet still containing the mass of a star. The universe around it is cold and nearly empty. Galaxies have drifted apart. Stars have burned out. The cosmic microwave background, once a soft glow, has cooled to near absolute zero. In this quiet darkness, the black hole begins its last transformation. As its mass shrinks, its temperature soars. Where once it radiated feeble whispers of photons, it now emits a storm of high-energy particles. The surrounding space flickers with intense X-rays and gamma rays. Time itself seems to speed up as the radiation grows ever more violent. The event horizon contracts, pulling tighter and tighter around the singularity. It is as though the very fabric of space-time is being wrung dry. Matter and energy, once trapped beyond hope, are finally released as pure radiation. Each second is hotter, brighter, and more chaotic than the last. For an outside observer, the black hole's final moments unfold in a breathtaking cascade of light. The darkness that once devoured stars now shines with the brilliance of 1,000 galaxies. In a single, cataclysmic flash, the black hole evaporates completely, its mass converted entirely to energy in a final blaze that lights the void. This is not an explosion as we know it. It is a quantum farewell, the ultimate expression of EMT, where every ounce of matter becomes a torrent of light. Afterward, no trace remains, no core, no shadow, only a fading wave of radiation racing into the infinite night. After the last flash fades, the universe absorbs the memory of the black hole's existence in silence. There is no crater, no lingering shadow, no remnant to mark where it once consumed stars and light. Only a faint ripple of radiation, stretched thin by the infinite expansion of space, drifts outward forever. Around this silent void, the cosmos continues its slow unravelling. Galaxies, already scattered across unimaginable distances, grow dim and cold. The few remaining particles wander through a space that has grown vast and lonely. Time itself feels different here, no longer measured by the rise and fall of stars, but by the whisper of entropy creeping toward absolute stillness. For those who ponder the far future, this is a vision of the universe in its final era, a dark age where black holes, once the ultimate symbols of permanence, have all evaporated. No light from distant suns, no galaxies to chart the sky, only thin radiation and a sea of elementary particles adrift in endless night. The death of a black hole is not a violent tragedy, but a quiet balancing act. Energy once locked behind the event horizon returns to the cosmos, as if the universe reclaims every borrowed particle. It is a reminder that creation and destruction are never separate. They are the same rhythm, pulsing through space and time, and in this rhythm lies a deeper truth. Nothing lasts forever. Not stars, not galaxies, not even the most powerful forces of gravity. What we call eternity is only a chapter in a story without end, a story written in light, silence, and the ceaseless expansion of the cosmos. When the final black hole fades into nothingness, the universe will not mourn. It will simply continue, carrying the echo of what once was, a memory of darkness transformed into light. Chapter 8. The Fate of Information. When the last black hole fades into silence, one question lingers across the void. What happened to everything it swallowed? Every star, every planet, every scrap of matter and energy that crossed its event horizon? Was that information lost forever? According to the laws of quantum mechanics, the answer should be no. Quantum theory insists that information cannot be destroyed. The position and state of every particle, every quantum bit of reality must be preserved in some form, even if transformed beyond recognition. But black holes appear to defy this rule. If a black hole evaporates completely, and its singularity disappears in a final flash, where does the record of all it consumed go? This puzzle is known as the black hole information paradox. First posed in the 1970s, it sparked decades of debate among the greatest minds in physics. Stephen Hawking argued that information might truly be lost, suggesting that black holes could erase the past, breaking one of the most fundamental principles of physics. Others disagreed, believing the universe could not allow such a violation of its own laws. One possibility emerged: the information is not destroyed but somehow encoded on the event horizon itself, like patterns on a cosmic hologram. As the black hole emits Hawking radiation, perhaps it releases not only energy, but subtle imprints of every particle it has devoured, information woven into the faint glow escaping into the cosmos. This idea, called the holographic principle, proposes that the three-dimensional universe we experience might actually be a projection of data written on a two-dimensional surface at its boundaries. Yet the debate is far from settled. Physicists continue to wrestle with the paradox, searching for a theory of quantum gravity that unites the laws of the very small with the laws of the very large. String theory, loop quantum gravity, and other bold ideas all attempt to bridge this gap, but none have fully solved the riddle. For now, the fate of information remains one of the deepest mysteries of the cosmos. A black hole's death is not just an end, it is a question about memory, about reality itself, and about whether the universe can ever truly forget. Physicists have proposed daring ideas to preserve the sacred law of quantum mechanics. One of the most striking is the firewall paradox, a radical suggestion that the event horizon is not a smooth boundary at all. Instead, it could be a blazing wall of high-energy particles that burns anything crossing it, destroying the notion of a gentle passage and encoding information in the violent flare. But this idea clashes with Einstein's general relativity, which predicts no such drama at the horizon. Others believe information is not lost but scrambled in a way that, while impossible to decode with current science, remains perfectly preserved. This concept of black hole complementarity suggests that to an outside observer, information hovers near the horizon and slowly leaks back through Hawking radiation, while to an infalling observer, it continues inward without contradiction. Both perspectives are true, depending on where you stand. Recent advances in quantum computing and the mathematics of entanglement hint at deeper connections. Researchers exploring the ER-EPR conjecture imagine that entangled particles might be linked by tiny wormholes, subtle bridges in space-time, offering a way for information to escape the black hole's grip without breaking the laws of physics. Meanwhile, observatories such as the Event Horizon Telescope capture the shadows of black holes like M87, and gravitational wave detectors record the ripples of their collisions. These experiments cannot yet read the information inside, but each new measurement adds pressure to the paradox, guiding future theories. In the end, the fate of information remains an open question. Perhaps the universe keeps every memory, encoded in ways we have yet to imagine. Perhaps black holes are not vaults of destruction, but archives, where the story of everything they consumed is etched into the fabric of space-time itself. What we know is this: black holes, once thought to be the final word in cosmic silence, may instead be storytellers. Even as they evaporate, they might whisper the history of every star, every planet, every particle they have ever touched, their final legacy a quiet proof that nothing, not even the past, is truly lost. Chapter 9. Observing the Invisible. If black holes slowly evaporate, where is the proof? Hawking's theory is elegant, but detecting Hawking radiation is one of the greatest experimental challenges in all of physics. The signal is so faint, so subtle, that even our most advanced instruments strain to find a whisper in the cosmic noise. The temperature of Hawking radiation for a stellar mass black hole is unimaginably low, far colder than the background glow of the universe itself. A black hole with the mass of our Sun would radiate at less than a millionth of a degree above absolute zero, hidden beneath the constant hum of the cosmic microwave background. Even a detector placed just outside the event horizon would hear nothing but silence. Yet scientists have not stopped searching. They build telescopes to chase shadows and ripples in space-time, hunting for indirect clues. The Event Horizon Telescope, a planet-wide network of radio observatories, captured the first ever image of a black hole silhouette in 2019, revealing the glowing ring of light around M87. Though it cannot yet see Hawking radiation, it proved that we can study black holes directly, not just in theory. Others turn to the universe's natural laboratories. They study black hole mergers through gravitational waves, faint tremors in space-time detected by observatories like LIGO and Virgo. These waves confirm Einstein's predictions, and each detection brings us closer to understanding how black holes form, grow, and maybe even evaporate. Some researchers experiment on Earth, creating analogues of black holes in laboratories. Using ultra-cold atoms, superfluid helium, or high-energy lasers, they mimic event horizons and watch for tiny bursts of radiation. These tabletop black holes cannot swallow stars, but they might reveal the same quantum effects that power Hawking radiation. Through each observation, science edges closer to proving that even the darkest objects can glow. It is a pursuit of patience, a quest that spans decades and demands technology we're only beginning to master. Despite the silence of Hawking radiation, scientists are not discouraged. They look to the far future and to the most advanced technologies humanity has yet to build. Space-based observatories, cooled to near absolute zero and shielded from cosmic noise, may one day detect the faint glow of a black hole's final breath. Next-generation gravitational wave detectors, sensitive enough to hear ripples far fainter than today's instruments, could reveal signatures of black hole evaporation long before the final flash. Some theorists even predict that small, primordial black holes formed moments after the Big Bang might already be evaporating. If such ancient remnants exist, they could release sudden bursts of high-energy gamma rays as they vanish. Astronomers are scanning the skies for these fleeting signals, hoping to catch one of these cosmic deaths in real time. A single confirmed detection would be a triumph, proof that Hawking's vision was correct and that no darkness is truly eternal. Meanwhile, Earth-based laboratories continue to create analog black holes using supercooled gases, optical fibers, and even sound waves to mimic event horizons. In these experiments, researchers have observed faint radiation strikingly similar to Hawking's predictions. Though these are not true black holes, they provide a rare window into the quantum processes at play and strengthen our confidence in the theory. Each effort, whether cosmic or microscopic, is a step toward the same goal: to witness the unseeable, to hear the universe's faintest whisper. It is a testament to human curiosity that we chase a signal that may not fully reveal itself for trillions of years. Perhaps one day, far in the future, when technology has reached unimaginable precision, we will watch a black hole evaporate with our own eyes. Until then, the search continues, a quiet, patient pursuit of the ultimate proof that even the darkest corners of reality cannot hide from the light of discovery. Chapter 10. The Black Hole's Legacy. When the last flicker of Hawking radiation fades into silence, the black hole is gone, but its influence lingers across the cosmos. For billions of years, these objects were not just destroyers. They were architects of galaxies, sculptors of cosmic structure, and keepers of ancient history. At the center of nearly every large galaxy lies a supermassive black hole. These giants, millions to billions of times more massive than our Sun, act as gravitational anchors. Their immense pull shapes the orbits of stars, stabilizes galactic arms, and orchestrates the dance of countless suns. Without them, galaxies as we know them might never have formed or survived. Black holes also regulate star formation. The colossal jets streaming from their accretion disks blast nearby gas clouds, sometimes compressing them to create new stars and other times sweeping material away to halt starbirth. This delicate balance between destruction and creation has guided the growth of galaxies for billions of years, influencing where stars ignite and where they fade. Even after evaporation, the legacy of a black hole lives on in the elements it helped scatter across the universe. The supernova that birthed it spread heavy metals like iron, gold, and uranium, materials essential for planets, for life, for us. Every breath we take, every cell in our bodies, carries atoms forged in the furnace of a massive star whose collapse may have given birth to a black hole. And so, when a black hole finally dies, it does not simply vanish. Its story is written into the very structure of the cosmos, in the paths of stars, the makeup of planets, and the quiet architecture of space. The darkness that once devoured everything becomes part of everything, a silent testament to the endless recycling of matter and energy. Through their lives and their deaths, black holes teach us that the universe is not static but a cycle, a vast, unending flow of birth, transformation, and return. Long after the final black hole has evaporated, its influence remains etched into the universe. Not as a scar, but as a subtle design, an invisible architecture that continues to shape the cosmic story. The galaxies they anchored will have dispersed, their stars extinguished, yet the echoes of their gravity persist in the motions of dark matter and the quiet drift of intergalactic space. For humanity, these ancient giants are more than astronomical curiosities. They are reminders of the delicate balance between creation and destruction, the gold in a wedding band, the iron in our blood, the calcium in our bones, all trace their origins to stars that once died in the same violent births that create black holes. In their collapse and eventual evaporation, black holes recycle the elements of life itself. They also challenge our understanding of time. A black hole's lifespan dwarfs every scale we know, from the fleeting moments of a heartbeat to the entire age of galaxies. To contemplate their evaporation is to confront deep time, where the future stretches far beyond the reach of human imagination. It forces us to consider a universe where even eternity is temporary. Perhaps the greatest legacy of black holes lies not in their mass or gravity, but in the questions they leave behind. They push the boundaries of physics, demanding a union of quantum mechanics and general relativity. They whisper of hidden dimensions, of holographic realities, of truths we have yet to grasp. Each black hole is a cosmic teacher, showing us that knowledge is never finished, and that even the darkest mysteries can spark light in the human mind. When we gaze into the night sky, the black holes we cannot see still shape the galaxies that hold those stars. Their invisible hands guide the orbits of worlds, their ancient deaths seed the next generation of suns. They remind us that in the grand cycle of the cosmos, nothing is lost, only transformed. The story of black holes is not merely about their death. It is about connection, between past and future, between destruction and creation, between the fleeting and the eternal. Their legacy is written not in darkness, but in the infinite light of the universe they helped build. Chapter 11. Heat Death of the Universe. When the last black hole vanishes, the universe enters a new and final era. No stars remain to burn, no galaxies shine. What's left is a vast, silent expanse of near-perfect darkness. This is the slow march toward what physicists call the heat death of the universe. Heat death is not an explosion, nor a sudden event. It is a quiet fading. Entropy, the measure of disorder, reaches its maximum, and energy is spread so thin that no process can create new structure or sustain life. Every star has long since burned out. Planets have frozen and crumbled. Even the smallest embers of radiation stretch into invisibility as space itself expands. The black holes were the universe's last engines of drama. For trillions upon trillions of years they devoured matter, bent light, and shaped galaxies. Now they too are gone, their hawking radiation spent. Without them, the cosmos loses its final sources of gravitational excitement. No more collisions, no more tidal flares, only silence. The remaining particles drift apart in an ever-expanding void. Protons may eventually decay into even lighter particles, leaving only a thin mist of electrons, neutrinos, and faint photons, spread across a space so vast that each particle is separated by unimaginable distances. The universe becomes a thin, cold sea of almost nothing, hovering just above absolute zero. Time continues, but change ceases. There are no more clocks because there are no more events to measure. The arrow of time, which once pointed from order to disorder, loses its meaning when everything is equally empty. It is the final stillness, the end of thermodynamic possibility. This is the dark era, the ultimate silence after a symphony that lasted billions of years, a universe with no stars, no galaxies, no black holes, just a vast, cold darkness, an endless expanse where even memory fades into the background radiation of eternity. As the universe drifts toward perfect equilibrium, the last traces of structure slowly dissolve. Stars are long gone. Galaxies have unraveled into invisible clouds of particles. Even black holes, once the eternal anchors of space, have given back their energy to the void. What remains is a thin mist of subatomic fragments spread across an ever-expanding cosmos. This is not a sudden ending. It is a silence that deepens over uncountable trillions of years. Entropy, nature's tendency toward disorder, has reached its maximum. No gradients remain to power motion, no heat differences remain to drive change. The universe becomes an endless, uniform expanse of cold, a place where nothing new can ever form. In this final state, time itself seems to lose its meaning. When there are no stars to mark a day, no planets to measure orbits, and no events to distinguish past from future, the arrow of time grows faint. Moments blur into one another until only the quiet expansion remains. Yet this is not a tragedy. It is the ultimate balance, the fulfillment of the second law of thermodynamics. All the matter that once formed galaxies, life, and worlds is still here, transformed into the softest whisper of energy spread evenly across the infinite dark. For us, imagining this distant future is like looking at eternity from the edge of a dream. We will not see it, nor will the descendants of our stars. But in contemplating this final chapter, we glimpse the deepest truth of the cosmos, that change is inevitable, that creation and dissolution are part of the same rhythm, and that nothing, not even the universe itself, remains unchanged forever. The death of black holes was only a prelude. The heat death of the universe is the quiet coda, a single note held for infinity, as the grand symphony of existence fades into a perfect eternal stillness. Chapter 12. Philosophical Reflections. When we imagine the universe's long journey, from the birth of stars to the quiet death of black holes, we are not merely studying physics, we are holding a mirror to existence itself. Every stage of this cosmic story invites us to ask the oldest questions. Why is there something rather than nothing? What does it mean for time to have a beginning and an end? Black holes are the ultimate paradox. They are born from violence, yet they inspire calm. They represent finality, yet their slow evaporation reminds us that nothing is truly permanent. To contemplate their life cycle is to confront our own impermanence, our brief moment in a universe that measures its life in trillions of years. In their silence, black holes speak of transformation. Matter that once burned as a star collapses into pure gravity. That gravity in time releases its energy back to the cosmos through hawking radiation, It is a cycle of creation and return, where even the mightiest forces must yield to change. From the smallest particles to the largest galaxies, the story is the same. Nothing is lost, only reshaped. There is a strange comfort in this idea. If the universe itself is a grand experiment in impermanence, then our own fleeting lives are part of a greater pattern. The atoms in our bodies were forged in the hearts of long-dead stars. One day, those atoms will scatter again, perhaps to become part of another world, another life. In the cosmic scale, our beginning and ending are not separate. They are connected by the same eternal rhythm. Standing beneath the infinite night sky, we are reminded of how small we are. Yet, through the lens of science, we are also vast, because the universe lives within us. The carbon in our cells, the oxygen in our lungs, the iron in our blood all come from stars that once died in colossal explosions. In a very real sense, we are the afterglow of cosmic events billions of years old. Black holes magnify this truth. They show us that even the greatest structures are part of an endless cycle of transformation. Their birth from dying stars, their quiet reign, and their eventual evaporation are not signs of destruction, but of participation in a larger pattern, one that connects galaxies, elements, and life itself. Some see in this a message of humility. Our lives, though fleeting, are threads in a tapestry so immense it defies comprehension. Others find hope. If even the darkest objects in the universe can give back their energy, perhaps there is no such thing as true loss. What disappears in one form always returns in another. In contemplating black holes, we touch the boundary between science and philosophy. They are both a challenge to understanding and a meditation on existence. They teach us that time is not an endless line, but a rhythm, that endings are not failures, but transformations, that silence too can speak. When we think of the universe's far future, the heat death, the quiet after every black hole is gone, we might feel a chill of inevitability. But there is a strange peace in knowing that everything, from the smallest atom to the grandest galaxy, plays its part in a story without a final page. The universe will continue, even when no stars burn and no black holes remain, and so will the echoes of every star, every life, every fleeting moment, woven into the endless fabric of space and time, a silent testament that nothing is truly lost.